Hi there, Miss Barber here. This lesson is titled Inverse Trigonometric Functions and Right Triangles. For a function to have an inverse, the function must be one-to-one. Since trig functions are not one-to-one, in fact they're periodic, they do not have inverses. However, we can restrict the domain of each trig function to intervals in which they attain all of their values and on which they are one-to-one. The resulting invertible functions have the same range as the original functions and are also one-to-one. The objectives of this lesson are: 1. Know inverse sine, inverse cosine, and inverse tangent functions. Be able to solve for angles in right triangles. And 3. Be able to evaluate expressions involving inverse trigonometric functions. Roman numeral 1. The inverse sine, inverse cosine, and inverse tangent functions. Domain of invertible trig functions. The sine function on the restricted domain, negative pi over 2 to pi over 2, endpoints included. The cosine function on the restricted domain, 0 to pi, endpoints included. And the tangent function on the restricted domain, negative pi over 2 to positive pi over 2, endpoints not included, are all one-to-one and therefore have inverses. Inverse trig functions and their domains and ranges. The inverse sine function is the function sine inverse, written sine superscript -1, with domain -1-1 endpoints included and range negative pi over 2 to pi over 2 endpoints included, defined by sine inverse of x equals y if and only if sine of y equals x. The inverse cosine function is the function written cosine superscript -1, read cosine inverse, with domain -1 to +1, endpoints included, and range 0 to pi, endpoints included, defined by cosine inverse of x equals y if and only if cosine of y equals x. And finally, the inverse tangent function is the function tan inverse, with domain the set of real numbers and range negative pi over 2 to positive pi over 2, endpoints not included, defined by tan inverse of x equals y if and only if tangent of y equals x. Terminology. The inverse sine function is also called arcsine, denoted by arc sine. The inverse cosine function is also called arc cosine, denoted by arc cos. The inverse tangent function is also called arc tangent, denoted by arc tan. Roman numeral 2. Solving for angles in right triangles. The inverse trigonometric functions can be used to solve for angles in a right triangle if the lengths of at least two sides are known. For the triangle presented, which inverse trigonometric function should be used to determine the measure of angle theta? The theta, we are giving a measurement for the length opposite the side and adjacent to the side. So let's use tangent. Tangent theta would be equal to 12 divided by 5. Then, using the inverse trig function definition, we can solve for theta as theta equals tan inverse of 12 over 5. We can also get the decimal approximation for our inverse trig values by using your calculator. To do so, let's push tan inverse. So we'll go second, tan inverse, and the value was 12 divided by 5, close parenthesis, enter, and now the approximate value we have for the theta is 67.38 degrees. Evaluate the expression, the sine of the tan inverse of 12 over 5. Let's begin by working inside out, so I'm going to relabel tan inverse of 12 over 5 as A. A is equal to tan inverse of 12 divided by 5. Now, using our definition of inverse functions, we can rewrite this as the tangent of A is equal to 12 over 5. Now let's draw a right triangle that represents this trig function. So here's my right triangle. I'll put the little corner in to indicate that that is a right angle. Label one of the interior angles A. The tangent is defined as opposite over adjacent. So from the interior angle A, the opposite is the length 12. The adjacent is 5. We can compute the hypotenuse by using the Pythagorean theorem. That is, this length that we need for the hypotenuse, okay, is going to be the square root of 12 squared plus 5 squared, which is the square root of 144, plus 25, which is the square root of 169, or 13. So now we have that measurement in case we need it. So let's see what happens. We have the sine of tan inverse of 12/5 is actually sine of A, because we renamed tan inverse as A. So now let's look at the triangle and find the sine, which is opposite over hypotenuse. The opposite of A is 12, and the hypotenuse is the length we just solved, which is 13. Now we have an exact value for this expression. Find the exact value of part A, cosine inverse of 1/2. I like to write this in equation form, so I would have cosine inverse of 1/2 equals some unknown. I like the letter A. And then we apply the inverse definition, and we get that 1/2 is equal to cosine of A. So now what we have to do is determine what A in the domain from 0 to pi can we have for cosine that gives us an output value of 1/2, and that turns out to be pi over 3. The cosine of pi over 3 is 1/2, and it is in the acceptable domain. Part B, tan inverse of 1. Again, I like to look at equations, so I'm going to write tan inverse of 1 equals, let's use a fancy Greek letter, beta. Okay. Now let's solve for the 1 by itself. So I would then get that 1 is equal to the tangent of beta. The question is, what degree or angular value in the acceptable domain will the tangent of that value give 1? And we know that that beta will be pi over 4. That is, the tangent of pi over 4 gives us the 1. Solve for angle B in a right triangle where B equals 10, C equals 50, and angle C is 90 degrees. So let's attempt to get a visual of this right triangle. I'll make a right angle and connect the endpoints. I'll put a little square in the corner to indicate that that is my 90-degree angle. We need to find B, so I'll call one of the angles B, and the side opposite B will be the length that we are given as length 10, and the side opposite the 90-degree angle is C, and that length is 50. Now we are solving for B, so what trig functions do we have? We have a measurement for the length opposite and a measurement for the hypotenuse, which tells us sine is our trig function of choice. So we'll say that sine of B is equal to 10 over 50, which we can just reduce to 1/5. But that doesn't quite answer our question. We need the angle value for B, so let's take the inverse function, and we get that B is equal to the sine inverse of 1/5. That still doesn't quite give us the degree measure, but that is an exact answer. Let's see how to solve it using a calculator. We are back in a TI-84 screen. We want the inverse sine function. So let's select inverse sine, which is the second button followed by the sine. That gives us the sine inverse. And the value that we are solving for is 1 divide 5. close parenthesis, enter, and this is degree measure 11.53695903, and the approximate value that we will write will be 11.5 degrees. A 96-foot tree casts a shadow that is 120 feet long. What is the angle of elevation of the sun? Again, I begin this by drawing a picture. So here is my tree, and we'll call that height 96 feet. It casts a shadow that is 120 feet. So we have a right triangle, and what we are concerned with is the angle of elevation theta that's supposed to be the sun, to the sun. And so we have a measurement for this theta, the length that's opposite to it, and one that is adjacent to it, which then lends itself to us using that the tangent of theta, which is opposite over adjacent, would be 96 over 120. We can simplify that a little bit and say that's tangent of theta is equal to 4/5. That still doesn't give us the angle of elevation that we need, so we've got to use an inverse trig function. We solve for theta, and theta is actually tan inverse of 4/5. Now we'll have to use some kind of technology to get an approximate degree measure, so let's do that. On my TI-84, I need the tan inverse key, so I'll push second, and tangent, which makes the tan inverse display. The ratio is 4 divide 5, press enter, and the degree measure is approximately 38.65980825. Let's round that to 1 decimal place for our purposes, and we will write that the theta is close enough to 38.7 degrees. Rewrite the expression, the tangent of the cosine inverse of x, as an algebraic expression in x for x between -1 and +1 inclusive. Let's see. We have the tangent of the cosine inverse of x. Let's work from the inside out, and I'm going to rename the cosine inverse is a. So a is equal to cosine inverse of x. Then applying the rule for inverse functions, we can make this so that cosine of a equals x. Now let's draw a right triangle that has these features. Draw the corner to indicate that that's a right triangle. I'll write A into one of the lesser angles to make sure that I know which one I'm talking about. The cosine is adjacent over hypotenuse, so the adjacent is x. The hypotenuse is 1. So now we'll use the Pythagorean theorem to solve for the side opposite A, which would be 1 minus x squared. So now we have lengths and measurements for all 3 sides. Let's continue with the initial setup. So we have the tangent of cosine inverse of x, and that turns out to be the tangent of a, because we said a is equal to cosine inverse of x. Now, the tangent of a, that's from this triangle, the tangent is opposite over adjacent. So the opposite is 1 minus x squared, and the adjacent is x.